We present a robust locomotion by logic framework, where we achieve perturbation-resilient bipedal locomotion via signal-temporal logic-guided model predictive control. In this study, we use formal methods to quantify the locomotion robustness and guarantee the completion of locomotion tasks. Specifically, we encode signal-temporal logic specifications into an optimization-based model predictive controller. The MPC runs online at 50 Hz. In the low level, a passivity-based controller with inverse kinematics functions tracks the desired trajectory from the MPC. We formulate an optimization problem to achieve two goals. First, it maximizes the satisfaction of the task specification. For stable locomotion push recovery, we design a specification that ensures the keyframe state eventually returns to a robust region in the planning horizon. The specification equation is illustrated on the right. Second, the MPC satisfies the self-collision avoidance constraints. These constraints are multi-layer perceptrons that encode the distance of collision pairs on the leg. These data-driven constraints are faster in computing both the distance and their gradients. They are also accurate compared to the ground truth. A planning horizon of 3 steps is shown in the bottom figure. We evaluate the MLP constraints by plotting their outputs at 5 distinct stance leg configurations. The landscape shows the collision distance between the 2 legs evaluated by the MLP constraints. Using the proposed MLP constraints, we generate a crossed leg maneuver. The right figure shows that the MLP constraints encode accurate collision distance and ensure the maneuver is safe. The bottom right figure shows the top-down view of the maneuver. We conduct a comprehensive perturbation recovery experiment and simulation. The Cassie robot is subjected to impulses with varying magnitude, direction, and timing. The plots on the right show that our STL-MPC can endure larger impulses than baseline methods, which are an A-lip controller and a linear temporal logic-based controller, especially in crossed-leg scenarios as indicated by the left half of the graph. Specifically, for a 0-degree perturbation toward the left, our STL-MPC initiates crossed-leg maneuvers to recover. For a 180-degree perturbation toward the right, our method achieves comparable performance with the A-lip controller. We test our STL-MPC's flexibility on more challenging terrains with disjointed stepping stones. Our MPC is able to select a proper foothold to proceed on. In addition, when subjected to perturbation, our MPC can change to another foothold and continue forward. We compare the solving speed of 2 encoding methods, a traditional mixed integer program method, and our method using smooth operators. The smooth method is significantly faster, and its solving speed is more consistent. To showcase the performance improvement offered by STL-encoded robustness, we compare the robustness of the solutions from our STL-MPC and a standard MPC without STL. The STL-MPC achieves higher robustness score across all tests and resists larger perturbations. We simulate ship motions to study the terrain-agnostic feature of our framework. We summarize the successful trials to different combinations of oscillations in a Bode plot of recovery capability. The Bode plot shows the STL-MPC's strong adaptability to the pitch axis oscillations. We also apply horizontal perturbations on inclined stationary surfaces and summarize the success rate of perturbation recovery in the heat map. Here we show 4 successful trials from the heat map. These 4 trials are Cassie walking on surfaces with different inclination and recovers from a 100 Newton perturbation. We implement the STL-based MPC framework on a bipedal robot Cassie and test it on Karen, a perturbation system. We show horizontal terrain perturbations in 4 directions, especially for the 180-degree trial with crossed leg maneuvers. The visualization shows the Cassie's real-time state and the MPC output trajectory. To analyze the robot's recovery strategy after perturbations, we plot the center of mass state in the phase space. The plots demonstrate our framework's ability to adopt stepping strategies based on various perturbations and recover within 2 walking steps. To test the maximum allowable perturbation on Cassie, we use a perturbation emulator. The emulator can generate a large and precise pulling force on Cassie's pelvis. The maximum tolerable force is shown in the spider graph, with 0 degree indicating perturbing to the left. To test the robot's terrain-agnostic walking ability, we use the Karen system to simulate ship motions, which include pitch and roll oscillations of the terrain. The robot can withstand perturbation up to 5 degrees for single-axis oscillations and 4 degrees for dual-axis oscillations. For the roll axis perturbation, the robot frequently adopts crossed leg maneuvers, indicating the significance of this motion for robust locomotion. We'd like to express our appreciation to our funders for their support, and thank you for watching.